before I introduce our final keynote speaker, I just wanted to share with the audience some recent news. It's related to ARPA-e, and the two organizations, ARPA-e and NYSERDA, have very similar goals and objectives. Is advancing technologies, to save energy, clean energy technologies, and so both leaderships, the leadership both at ARPA-e and NYSERDA realized this, and we executed a memorandum of understanding to work together to stimulate the development of high potential, high impact, clean energy technologies. And that MOU, involves us sharing information, serving on each other's TEPs. But in support of that, NYSERDA has issued a funding opportunity, a program opportunity notice 3249. It's titled Advanced Clean Energy Exploratory Research Funding. And so what that, it's an open enrollment. It's you could submit a concept paper anytime, and it will take any type of idea that's transformative, high impact, but it also will consider funding for proposals to federal agencies, particularly ARPA-e. So if you are contemplating or you're responding to an ARPA-e funding opportunity, there is this opportunity for us to support that effort with funding from NYSERDA. And so the way you would do that, you would submit a concept paper. We review, we get it back to you, we support that. It's intended to build on the funding that ARPA-e is providing if you get selected. And also, if you have a pending award from ARPA-e, you can actually submit a request to NYSERDA for additional funding and to build on the ARPA-e activity. So this is all in the spirit of working together, collaborating, and in trying to advance clean energy technologies. So let me introduce our final speaker. Jennifer Gerbi is currently the program director at ARPA-e. Her interests are in improving energy efficiency and management via advanced sensing systems, localized heating and cooling, and renewable energy generation via photovoltaics. Prior to joining ARPA-e, she worked for Dow Corning and the Dow Chemical Company. And from 2007 to 2011, she served as a senior materials scientist at Dow, developing SIGS photovoltaics for rooftop shingles. And recently, at Dow Corning, she led a electronic application engineering and development team working directly with large global customers to enable electronic solutions in customer and crossover healthcare markets. She holds a PhD in materials science from the University of Illinois Urbana-Champaign, and an MS in physics from the University of Virginia. So with that, I'd like to welcome Jennifer.
Thanks so much for that introduction. It's really been a pleasure to be here. I really appreciate the invitation to speak. And I have to say that when I've looked through the catalog to see which talks there were yesterday, unfortunately I couldn't be here yesterday, and today, I'm really struck by the different types of technologies and applications that people are looking at and working on together. This type of a symposium, I think, is exactly what's needed to bring teams together that are working in different areas. And I'll talk a little bit about ARPA-e and why we're that way as well, because you can't have a solution in a vacuum. You don't want to work on technology that's not going to have an impact, right? And there's a lot of different things you can do to make sure that the technology you're working on can have an impact. I'm not going to punish you guys by staying here by going over, so I'm basically going to give about half of the talk that I was going to have, which is fine, because a lot of you already know about ARPA-e and have even probably seen a lot of the slides that I'm going to show. So I'm just going to talk a little bit about ARPA-e. So ARPA-e is a small agency within the DOE. We sort of have our own rules. We're like DARPA, but we're much smaller than DARPA. And so what we do is we try to find high-risk, high-reward technologies, usually that nobody else will touch, and try to figure out how to put together a program around $35 million to solve a key problem. We are very big on impact, and what impact means is that somebody's gonna have to make what you end up developing, and somebody's gonna have to buy what you end up developing. So the market is intrinsic to what we're doing when we start to develop some crazy new technology that nobody's ever thought of before, or that nobody could get to work before. From day one, we consider the market along with the technology, and that is why our programs are successful. It can be hard to convince people to do this. Definitely in my past, I've had experiences where I was in a technical group where we literally were not allowed to talk to the marketing group. They put them in a different building in a completely different campus and said, you are not allowed to talk with them. When I decided to leave that company, I decided to go talk to them and learned a lot of interesting things about cost models and assumptions and how you can prove something will never work because nobody will ever buy it. I'm not saying who it was. You don't want that to happen, right? And so that's why from day one, you have to have this multidisciplinary approach, multifunctional approach. And that's one of the reasons why things like this are so exciting, why this center at Syracuse is so exciting, because I think that you guys do that. And I think that we need to encourage that kind of work more. So it's really a pleasure being here, and it's also a pleasure working with folks from here. Obviously, you know, Ez has one of the projects from Delta, and I'll talk about that a little bit, and he talked about that today, okay? So I'm gonna actually skip a whole bunch of slides. ARPA-E is pretty young. It hasn't been around all that long, but we've grown quite a bit. You want a disruptive learning curve? We'd really like an impact. See, I can go through these pretty quick. Solving problems is hard. I think that's really important to realize. When we go through developing a program, it takes about a year before we even give a pitch to the agency. That's how much work goes behind actually defining a program. This is our portfolio, and I'm going to stop here for a second just so you can see that we have stuff all over the map. We have programs in solar. We have programs in biotechnology in terms of, you know, growing crops to use for alternative fuels. We have some energy efficiency savings technologies. We have battery technologies. It's all over the place. We have a root phenotyping project for carbon capture. I mean, we do a lot of different things. And all of us sit in a room together and vet these programs. So you have PDs from all different backgrounds coming together and watching a talk about biology, for example. It's fascinating. Part of the reason I'm telling you that is a little plug that if you're interested in working there, we are always interested in hearing from people that would like to work there. So again, moving technology towards market, I'm going to skip all of these. In terms of resources, this is a useful one, and this is one of the keys about why ARPA-E is such an exciting place and why we're successful, is that the people that come up with the programs are the ones that manage the programs. And you can ask Ez about this. We are very hands-on in terms of program management. So if you've developed a program, you are managing all of those projects very intensely. So you will go through the data, you will ask all the hard questions, you do this quarterly, if not even more often, very active program management. You're not handing it off to someone else. And that is one of the reasons why this works so well. And you want it to be successful, and you will help them be successful. The other thing we can do is we're very flexible. So we can actually pivot a project, we can cancel a project, which we need to do often because it's high-risk research, and sometimes it doesn't work. But sometimes you can pivot to something else. We can plus things up. Oh, it's going great. Here's another year of funding so you can do a field trial. Things like that. So that flexibility is really exciting. There's a high bar. I mean, you don't get $2 million more just because you ask for it. But if all the other PDs agree and the director does, then you do. So that's really fun too. And this slide is very important. Tell your friends who left early. The ARPA-E Summit is fabulous. That's actually how I found out about ARPA-E. It's huge. There's all sorts of people there, from policy to market to inventors. All of our project teams go. We have demonstrations. It is such a dynamic meeting. I honestly have never really been to something like it. I was very lucky because the first one I went to had Bill Clinton and Bill Gates. So that was pretty cool. So if you can swing it, I heartily suggest going to this. I've met people that I ended up collaborating with that I never would have met otherwise. So it really is, it's exciting, and it's not just because it's ARPA-E, it's a particular event. So I definitely encourage you to go. Again, recruitment opportunities, we have program directors like me, we have tech to market advisors, which are heavy in the market, that would be on my team. We also have fellows, which are recent PhDs, and that can be really interesting. If you have any interest in this, shoot me an email and I can send you to the right person. So let's go to Delta, let's go to an actual program. And the point of Delta is you want to heat or cool a person instead of the building. So you can extend your temperature set points of the building if your person is comfortable inside. Some people call this put on a sweater program. So when you make it colder, honestly, it sort of is a put on a sweater program. But when you make it hotter, how do you cool off? That's the hard part. You can put in a space heater, as many people do, but nobody has a space heater that actually makes you cold. Well, unless you're talking to Ezra, that's exactly what he's making with phase change materials. And so we have a couple projects around that. And so it turns out that you can actually save a lot of energy by doing this. This is a big pie here, and what you see here in terms of 13 quads, 13% of the energy that we spend out of all of the energy goes into commercial and residential heating, cooling, and ventilation for people. That doesn't even include manufacturing, okay? So you can actually make a very big impact even by changing that percentage a very small amount. We usually consider one quad as sort of the benchmark if a program is interesting. You have to show an impact of at least one quad. And you can have a multiple quad impact when you start looking into this area. So again, the objective is to increase those bands so that you can save energy. We're in about Q5, Q6, so this program has been developed. It was developed a couple years ago by another program director, and I took it over last year. You can calculate how much power a person basically puts out in terms of heat, and then how much power that you have to basically put back to cool them, for example. So we do have some metrics around the power of the systems that we're using. And, you know, again, to Forrest Megger's talk, actually, when you think about it, most of the heat that you lose is through radiation. It's not through convection. It's not through evaporation. So we have some technologies, for example, in smart fabrics that change the amount of IR that is either reflected back to the person or actually transmitted out the clothes. And you can change that. And that can help you be comfortable in a situation, or that can help you be warmer in a situation where you would have been cold. The goal is to be able to integrate this into clothes you'd wear into the office. So here's our portfolio right now. And when you look at the categories, this idea of extended energy range transfer, so this near energy range transfer and extended, those are sort of the same things. Those are sort of the PCM type of, say, local air conditioners. And then we have a lot of wearable technologies, and those are the smart fabrics that maybe they have pores in them. Maybe as it gets colder, the fabric actually gets thicker. Things like that. Some things that are actively controlled, some things that are completely passive. It's really interesting to see what you can do with fabric. But from a market point of view, this is really hard because you're talking about garments. And when you talk about what the requirements are for a garment, that's not something that we usually think about in the lab when we're trying to get a thermoelectric to work or something like that. So this is a really interesting program from that point of view, and we're doing very hard work to try to make sure that we are integrating the market side right along with the technical side. And I can talk about the projects. Again, I'm going to skip through most of these, but I do want to show one, and this is something that Ez mentioned in his talk. So a group at UMD has a system that uses phase change material, so it can be a local air conditioner. It's on a robotic platform so that it can theoretically follow you around. This thing got so much press that we've decided there has to be a robot in every program, because once you have a robot, everybody wants to talk to you. Unfortunately, robots are really expensive. So when you actually do the cost calculation, does it really make sense to have a robot, or can you just pull it around on casters to wherever you want it? There might be different versions of this. But the point is we have the freedom to do that. And a lot of work goes around that nozzle that they're using and put a plume of air around a person. And it's very interesting to think about using this in warehouses or in spaces where you only have to heat or cool a few people instead of a giant space. It can be enabling for that, for doing maintenance in certain areas. Again, so if you have a building that has very low occupancy, something like this gets very, very interesting very quickly. And then if you look at the project here, the idea here is that you'd have something that's actually fixed at a desk. And it's amazing engineering that they've done with this, and inventing a new compressor, which I saw running today, which I just love, and it's almost completely silent, and it's really interesting. So you could feasibly have this in offices. But again, it makes a little bit more sense to have this in an office that's a little bit more sparsely occupied than one where you have a desk every foot. So you can think about different types of buildings and situations where this makes sense. or buildings where you have a floor and a half that are occupied and 10 floors that aren't. Well, you don't need to heat or cool the entire building the same way. And so I'm going to skip through most of these. Again, a lot of these either use IR or sort of an oxidic material so that, again, it gets bigger when it gets colder. This one from SRI, this is an old picture. What they're actually making is a water-cooled boot with a radiator, so your boots will get colder to cool you down. There's ones that use thermoelectrics. There are ones, again, that use IR reflecting material. So we have all sorts of projects in here, and every one is interesting in its own way. And so we have a lot of partners that are interested in this program, and one of the things we do is we try to get more partnerships developed, more commercial partners in to help make this successful. So that is a program that's a little bit different than programs we've done before. When you think about a garment, we don't think we've ever done anything involving a garment before. So I have a little bit more time. Again, I promise to go pretty quickly, but I did want to talk a little bit about a program concept that's in development that I've been working on for almost a year now. And so hopefully there'll be a decision on this relatively soon. And this is to reduce the amount of HVAC that you use via true occupancy sensing. So when you think about it, what happens when you're not at home? For most people, they're heating or cooling their house just like as if they were home. That's a problem. What happens when you're not at work? When you're not at work, it's even worse. When you're not at work, not only is that building being cooled or heated, maybe there's a little bit of a setback, but it's ventilated. And it turns out that ventilating those buildings actually takes more energy than heating or cooling the buildings, and it's getting worse. It's getting worse because we're learning that cognitive abilities suffer at lower CO2 levels than we originally thought, and one of those groundbreaking studies was done here. So the push is for more and more and more ventilation, doubling the ventilation, without having any data to say whether or not you have to do that. If a building designed for 2,000 people, there's 3 in it, and it's ventilated for 2,000 people. You can save a lot of energy by changing that ventilation level if you only knew how many people were in the building. And this turns out to be a really hard problem. We need this data. We need the data to say how many people there are. And again, I'm showing this pie again because I'm attacking this 13 quad piece of pie, and you can save a lot of energy if you can address this issue. So the reason this is exciting is because you waste so much. So if you even have a 7.5 reduction, which is actually very small, you can save a quad of energy. There's been a lot of work done and studies done that show even if a programmable thermostat worked right, you would save 30%. So 30% is actually the number that we're going after here. And again, looking at where this energy goes, most of it goes towards heating in a house, so 5 quads versus 2 quads, no ventilation. Again, and these numbers are from 2012. Finally, ventilation has surpassed heating and cooling, and actually these numbers are probably undercounting, and actually they're probably worse now because people are actually increasing their ventilation instead of decreasing it. So the other reason this is interesting is because you can change ventilation relatively quickly, but there's such a large thermal mass in large buildings that turning the heat up or down, it takes a long time for that to recover. So ventilation is something you have more freedom to change on a shorter time scale. And so I just want to, again, emphasize these systems are so simple, especially the residential systems. We have the controls already to understand how to do this. Even if you have a heat pump system, we have the controls to figure out how to do this. Everything goes back to a thermostat. How is this problem not solved? Well, let me tell you somebody who started to solve this problem. So the Dutch in the 1620s figured out the first thermostat, which was a simple mercury switch to keep the eggs warm in an incubator. And then the Scots figured out, well, if we use a CTE mismatch of 2 materials in a bimetallic strip, that strip will move depending on what temperature is, and we can actually use that as a thermostat. And then in my house this year, I took out a thermostat that uses both of these technologies. And I will tell you that that thermostat was actually easier to set than any of the thermostats that are on the market now, okay? So there's an interesting quote here, and sorry this is a little bit long, but I love this quote from the 1800s. Few housekeepers are philosophers enough to be willing to undertake the management of a machine requiring a mental effort, thinking at all, where the advantages are not directly visible to the senses. When you are gone from your house, you don't know how hot or cold it is. Most people don't really look at their energy bills, and you certainly don't know how much ventilation there is in a building going on. That is truly invisible. So even back then, people realized that this was an issue, and this human behavior issue is not going away. So programmable thermostats were supposed to solve this problem, and they were a dismal failure. And they're a dismal failure because of the human interface problem. A lot of people have studied this. Alan Meyer, for example, spoke at my workshop, and I've talked with him. And these are actually getting worse. I mean, it's really difficult, because before I could just turn the thermostat up or down if I wanted to change it, and now I have to push 6 buttons in succession. There's been a lot of studies that showed sometimes these even made it worse. People used more energy than even just leaving the thermostat alone. So we have to be pragmatic and say, this didn't solve the problem. What if we had a thermostat where you didn't have to ever touch it? So that's something like what the Nest tried to do, right? It tries to learn when you're there. It tries to figure out an algorithm so you never have to touch it. Unfortunately, it doesn't work very well. Apologies to Nest, and I know that they're working on it, but part of the problem is they don't have the data they need to say when you are truly there or not. So if you're sitting in your office and your AC turns off, when that happens once, you're angry. When that happens twice, you're probably not going to keep using that thermostat in the same way. There is very, very low tolerance for false negatives. Now, if it turns on when you're away, that uses more energy and you're not going to save as much money. So then you'll sort of get angry. There's actually a lawsuit about that right now. But it's not as enraging as when you're home and it turns off, okay? So that's why we actually need true presence sensing and not movement sensing. Even when it's coupled with a few other things, you can still get those false negatives. So we want to develop sensors that have an extraordinarily low false sensitive rate, that are super cheap, that you can peel and stick, put wherever you want, and that interface with existing control systems, whether it's a thermostat or something else. We want this occupancy sensing. I want to know there's 2 people on floor 4 and 1 on floor 3, or a whole bunch of people on floor 1. If we have that information in a commercial building, we can now actually do ventilation, demand control ventilation, and we can actually save a significant amount of energy. There's a lot of studies that show a lot of different ranges for what you can save. They're all higher than 7.5%. So even just looking at ventilation alone, you can save over a quad of energy. And I don't want to talk this too much, but this is something I learned at Dow Corning that I really liked. It's sort of this design thinking thing. But something has to be feasible, viable, and desirable. So the technology has to work. You have to be able to make money making it, and somebody has to want to buy it. So the way we do that at ARPA-e is we have technical metrics in a FOA, we'll have cost metrics in a FOA, and customer requirements, which might be soft metrics in a FOA. If we address all 3 of these in the right context, then it will work and you will have a big impact. So when we think about writing a FOA or developing a program, this is the way we think about it, and this is the reason why it can be successful. And so that's, again, one of the things that I love about ARPA-e. It's one of the reasons why it's great to work there, is because we do look at all of these things together. And again, this is the type of technology we're talking about making. Oh, I want to bring up my Amazon Dash button. For those of you who have not seen an Amazon Dash button, this thing which is $5 and then free later, and you push the button and then you just order detergent. This is powered by a AAA battery. It has a Wi-Fi radio in it. It has memory in it. It has a microphone in it. And this is very, very low cost. These types of low power electronics platforms are the reason why these types of sensors are going to be able to work, because those platforms are available now. Okay. And I'll just go ahead. So basically this is at the end. So where do we go from here? When we have all this information together, just to let you know, we go through, we develop metrics, we put an internal pitch to the agency, we reach out and we talk to 200 different people, and then we move forward and craft a FOA. So I'm not doing that yet, so I can still talk about it, but hopefully pretty soon I'm not allowed to talk about this at all anymore. So if you have any questions, feel free to ask me, because pretty soon I don't think I'm going to be able to answer them. Okay. So thank you very much. Again, I really appreciate the invitation. It's been a pleasure to be here. Thanks.
Thanks so much. Questions?
So Jenny, I
Here's your
know
chance.
Tim Labreche was at the workshop that you held a couple months ago in Portland to discuss what are the ideas behind this. Can you talk a little bit about the results of the workshop? What did the people in the community think was the best sensor technology? You know, is it going to be some kind of audio thing, visual, what?
That is a great question. So I would say that there are probably 12 to 14 different technologies that people like, and everybody sort of likes their own potential technology. So there wasn't a consensus coming out of that workshop about what the right technology was. I think the consensus was more about, we need this technology. It would be really useful. It really helped us define what some of those customer requirements are. For example, one was legal and thinking about things like wiretapping laws. I never thought about that before. So a guy from GE told us about that. That was interesting. There's a lot of people trying to put these in luminaires, and that has a lot of challenges about putting occupancy sensors in luminaires, and so we talked a lot about that. So it really helped us frame a lot of these soft metrics in the FOA and understand who the end users are and things like that. If I write this, it's going to be completely technology agnostic. We're going to have metrics. Here's what these sensors have to do. Here's what your budget is. But we're not going to say what the technologies are. And I hope that we're very surprised by some of the applications that we get. We'll see. So what we do is we do a top-down calculation by if you save a certain amount of energy. So we're going to have it at, I'm sort of not supposed to talk about this, but let's just say you pick a certain percentage of energy you're going to save. We calculate it with a 1-year payback, and we say, here's the system budget. So that system budget includes everything. So you can break that system budget now down to say, depending on how many sensors you have per square foot, you can calculate a cost. And so some people might have a sensor where you need only 1 per room like this. Some people might have 20. And so those costs will be different. So it comes down to this overall top-down budget. Anybody else?
In your diagram, occupants on a third, second, and the first floor, going back to the safety issues, when you have a fire drill, you're supposed to know how many people are in the building.
That would be nice. I don't think most buildings know
You have
that.
to fire people, and they'll, that's the first thing they'll jump on you for. But if you use their criteria, at least if you get to the 5% mark, you certainly get a reduction.
I mean, it's an interesting point about being able to use this information also for security purposes, for example. That's a very good point. I know our building doesn't do that. And even buildings I've had to badge into, they didn't do it that way, even if they should have. But it's important, that's a good question. And the other issue is, buildings that have zone control. It's amazing how many old large buildings don't even have zone control. So there's a limit to how low you can put the ventilation in a building like that.
The newer buildings had home run ducts supplying returns. That's one way to control your HVAC and variable frequency drives.
Mhm. Right. And I should mention, something I didn't mention at all, but that we're very interested in, is that we are going to have as a requirement for this, if it moves forward, that you also have to have CO2 sensors. And having cheap, wireless CO2 sensors that don't drift and actually have an accurate number is something that we also would want to have as part of this program. Because I don't think that anybody's going to buy a demand-controlled ventilation system that reduces the amount of ventilation you have unless you can assure people that the CO2 levels are where they want them to be. I see those two things as really intrinsically linked because, again, these indoor air quality issues are something that aren't going to go away.
In our research, we replace these CO2 sensors like every year because the cheap ones, I can buy 20 of them and then they drift and then you can buy new ones, right? Or you can buy the $10,000 one that doesn't. So did anybody, so the question I guess is, fundamental research of developing a sensor for CO2 is sort of outside of the building tech domain, right? It's like in the microelectronics domain.
So for us, it's completely within scope because even the cheap, it depends on what you mean by cheap. So when you look at sensors that need to be recalibrated every year and have a 3-year warranty, those are still $400 and they're $1,000 to install because they're wired. So first of all, when you go to wireless, your budget completely changes. You can't go to wireless with the current systems because of the way they are with the light sources, the non-dispersive IR systems. You don't have a $10 CO2 sensor that you can peel and stick to the wall. That's what we want.
So what about VOCs?
So that's a very good question. We talked with quite a few people about this, and it's a little bit of a can of worms when you start talking about indoor air quality. So we've talked about CO2 as a marker for whether or not your ventilation is sort of in the right range. We're not talking about measuring all VOCs for indoor air quality because we talked with some folks from companies that can do this, and if you want to do that, it will cost $47,000 a room because they do this in ships. We're not talking about that. This is not an indoor air quality program. What we're saying is for user acceptance, they at least need to know what that CO2 number is. So it's sort of a marker for quality, but it's not actually measuring, because you can talk to, I think, 5 different people and get 5 different ideas about exactly what you should measure for indoor air quality. So we're not going to go there.
Can you comment on the relationship between potential implementation of delta concepts in conjunction with occupancy sensing? Are there occupancy sensing solutions that apply to localized thermal amenities? Because they're sort of related, right?
Well, they're certainly complementary systems. So, I mean, it would be lovely to see those systems together. But again, delta, for example, has nothing to do with ventilation, and this has everything to do with ventilation. So I see them as very, very complementary types of systems. The other thing that I didn't mention is that we're very excited because if you have occupancy data, especially in a house, that increases your ability to use demand response programs. So we've talked with some utilities who are very excited about this, because if they know which homes are occupied or not, then they can utilize their demand response technologies in those areas. And so that's something where we're not going to include that in the numbers, but that's something that people are excited about. Okay.
More of a program question. ARPA-e has been around for a few years now, right?
Mhm.
You know, what's your success rate in regards to the project that they resulting in a commercialized product?
Boy, is that a good question. We struggle with that a lot because a lot of our programs have a long timeline to commercialization. So we have a portfolio, and that number varies a lot. So if you don't expect getting a commercial product for 15 years, and the agency's been around for 9 years, how do you quantify that impact? And we spent a long time actually trying to quantify our impact. So follow-on funding is one of the metrics that we use for impact, because it says, look, this technology's still alive, there's external interest in it, and we can quantify it by how much external money it got. So I think we're either just about or just surpassed $1 billion in follow-on funding for all of our programs. But we actually put together this book of impact sheets from specific projects, and to say, here's what the impact was and how we quantify it, and we work on those all the time. So believe me, being in a federal area, we have to do this sort of thing all the time. So we're always on the lookout to understand, how did this end up as a product? How was this made commercial? And something like what I'm proposing would have actually a pretty short timeline to commercialization. I would love to see something be on the market in 4 years, for example. It might not be the best of things, it might be the simple binary one, but it would be close to commercialization. But some folks are working on things that really are 20 years to commercialization. And so when your agency is young, you have to just do your best to look at things like that, look at IP, look at if a company got bought by another company, things like that. So that's actually, it's a tricky thing when you're young. It's a good question.
Has anyone looked into just counting occupancy using connections to a wireless access point?
So that has actually, and this is one of the tricks, because there's no global way to really measure this, and when people say how accurate something is, they don't tell you false negatives versus false positives. That would be considered a beacon in my book, because you're actually looking at a phone and not at a person. So it's very easy to miss a person who doesn't have a phone on them, or if they leave the phone in one zone and they move to another zone. So actually that is not an acceptable way to get occupancy counting at the number that we need to have it at to either quantify our energy savings the way we want, or to have almost 0 false negatives. So there are people that try to use that in a multimodal way. I think that Nest is doing that now, actually. So in very specific scenarios, I would say it definitely does help, but it's not at the technical metrics that we want to really have the impact that we're looking at. So saying no beacons at all is definitely something that's challenging, but then that will cover everybody. That's a much more flexible type of technology. But believe there's a lot of papers out there of people doing that.
Is there anything else across the world, in other countries maybe, that is a good example, or?
I mean, there's a lot of people that have ideas about how to do this, and we have looked very, very hard, and we haven't found anything that can actually do this yet. Now, if you're DARPA and you have $1 million to spend on a building, and you're gonna put $10,000 IR cameras in every room and then have somebody watch that camera, yes, you can figure out how many people there are in a room. But if you're actually trying to do this on the scale where it makes sense to buy from an energy point of view, or even something like a productivity point of view, that does not exist yet.
So DARPA funded a solution that there's a radar truck that comes by
Yep.
outside and counts
I heard about the radar
people
truck.
breathing. So
Well, and disaster response also looks at technologies like this, where if you can see an oscillation that looks like a heartbeat or breathing, that you know somebody's there. Those technologies are at least 3 orders of magnitude more expensive than what we're looking at, so they can't have an impact in this space. But believe me, we look at those technologies and we ask people, well, can you even think of a pathway that you can change this technology to be somewhat feasible? So through the wall, RF, Doppler or time of flight, we absolutely consider things like that. We good?
any other questions? Going once, going twice. It's a
Probably dinner time.
symposium.
Yay!
Thanks to you all for crossing the finish line. We look forward to seeing you at our monthly research and technology forums and other activities through the year, and we'll see you again next year. Thanks.